Okay, we're going to wrap up our discussion on limits with two separate topics, infinite limits and limits at infinity. Infinite limits is always taught with limits. This is basically vertical asymptotes. So here's a secret that calc teachers don't want you to know. Vertical asymptotes. Okay, this is when the graph increases or decreases without bound as you approach a certain x value. You learned about vertical asymptotes probably in Algebra 2, definitely in pre-calc when you're graphing rational functions. Discontinuities were either holes or vertical asymptotes. So we're going to talk about vertical asymptotes. Limits at infinity actually comes usually later in a calc book when you're talking about curve sketching. And here's a big secret. This is horizontal asymptotes. Another topic that you learned at some point in probably Algebra 2, again, maybe pre-calc, and this has to do usually with the degrees of the top and the bottom. And just to get us started, I've included a picture down here that has both. This graph has vertical asymptotes at -2 and at +2, and it has a horizontal asymptote at y = 2. All right, we're going to talk about how you can look at a function and determine its asymptotes, but we're going to call them limits now because we're in calc, we're not in Algebra 2. Okay, let's start with some infinite limits. These are limits where the answers are going to be infinity. And these are the vertical asymptotes. Now, you can look at a graph and very easily determine the limits. And if the line is going upwards, it's a vertical asymptote. The answer is infinity. Downwards, negative infinity. But we need to be able to determine that information without seeing the graph. So this first example, I'm approaching -1 from the left. Now, from the left is values slightly smaller than -1. Okay, -1 is an issue because -1 makes the bottom equal to 0, and that makes the top not equal to 0. And number over 0, if we were just to sub in the number -1, we would get 2 on top and 0 on the bottom. Anytime you get any number divided by 0, that's an indication of a vertical asymptote and a limit that's going to equal infinity or negative infinity. So how do we figure out when the graph approaches this vertical asymptote, is it doing so in an increasing or decreasing way? So here's the logic you need to do. A number, we're approaching from the left, so a number slightly smaller than -1, such as -1.0001. We want it to be close to -1, but we just really need to have a number slightly smaller. If I substitute this number on top, -1.001 squared, when I square that number, I get a number that's slightly bigger than 1. Very technical term. Slightly bigger than 1 plus 1 on top. On the bottom, I get a number that is slightly bigger than 1 minus 1. And that's really all you need to think about. You don't need to think about what number you're subbing in. You don't need to think about what the actual value is when you square it. We are only worried about whether this fraction is positive over positive, negative over negative, or one of each. So if I have a number that's slightly bigger than 1, because all squared numbers are positive, and I add 1 to it, I get something slightly bigger than 2. But that's positive, let's just call it 2-ish. Positive 2-ish on top. It's going to be 2.000 something, depending on what actual number we subbed in. But the important thing is that it is positive. Now, on the bottom, I plug in a number that is slightly bigger than 1, and I subtract 1 from it. So this is positive 0.000 something, 0.000-ish. The only important thing to know is that they are both positive. Positive over positive equals positive, and the result is positive infinity. Now, make sure you understand this. When we say the answer is infinity, we are not saying the limit exists. we are saying that this is a vertical asymptote and the graph is approaching positive infinity. It's more descriptive than saying does not exist, because that could be a jump or a number of things. We are saying infinity, but it's another way to say does not exist. Okay, so let's approach from the negative side, or excuse me, approach from the positive side. What if we are approaching one with a number like negative 0.999? And again, that's not it doesn't matter if I do 0.9 or a bunch of nines. I just need something a little bit to the right of negative 1. All right, when I square that number on top, I'm going to get a number slightly smaller than 1, but positive. And I'm going to add 1 to it, and I'm going to get something positive and slightly smaller than 2. Okay? Up here, I was a little bit bigger than 2. This is a little bit smaller than 2. On the bottom, I'm going to get a number slightly smaller than 1 when I square positive 0.99999. So this much is a little bit smaller than 1 and positive. Anything squared is positive. So that little positive number that's a little bit less than 1, when I subtract the full 1 from it, I get negative 0.000-ish. I get a tiny number, but it's negative. And again, the only thing that matters is the plus or minus. This is a positive number over a negative number, which means negative infinity. A more descriptive way to say does not exist. So what this tells me, in a vertical asymptote situation, we could have 2 graphs going upward, we could have 2 graphs going downward, or we could have 1 of each. What I've found out here is that this function, when it approaches negative 1 from the left, goes to infinity, and when it approaches negative 1 from the right, it goes to negative infinity. Okay, so that's how you kind of think this out. This is not a precise calculation. It's just an investigation to look at plus or minus. Okay, so here's a graph of that equation that we were just talking about. The x value in question is negative 1. For the reasons we talked about on the last slide, this graph is approaching positive infinity from the left, negative infinity from the right. We could have that same discussion about positive 1 over here, but we were just focused on the negative 1, so there's a picture of it just to confirm what we saw on the last slide. Okay, so here's one to try. I encourage you to pause. This function's a little bit simpler. See if you can tell me what this limit equals, and then resume for the answer. All right, so think about numbers that are close to 0. All right, I don't have a plus or minus. This is not a one-sided limit. This is just, are they both going the same way or not? So the limit at 0. If I plug in a tiny negative number, because the bottom is squared, I get 1 over a positive tiny number. And both of those things are positive, so I get positive over positive, which means if I'm coming in from the left, this thing's increasing to positive infinity. If I'm coming in from the right, also increasing to positive infinity. It doesn't matter whether I sub in a positive or a negative number. This thing is always positive. X squared is always positive, which means this thing goes to positive infinity from both sides. So we can say the limit is infinity. It's just like when we started talking about limits. If they didn't match, if you had this and this, we would say does not exist. If you had this and this, you would say negative infinity. And this is for a full limit, not a one-sided limit. If they match, we'll use the proper term of infinity. Still not saying it exists, but being more descriptive. This particular example looks like a volcano. The limit is positive infinity. All right, there's a picture of 1 over x squared, just to get a good visual, a nice neat graph. The limit from the left is infinity. The limit from the right is infinity. So therefore, the limit as x goes to 0 with no left or right also equals infinity. None of them actually exist, but since they match positive infinity, we can say the overall limit also positive infinity. All right, so let's change our tune. That was infinite limits. This is limits at infinity. The difference here is infinity is happening in the question. It's a horizontal asymptote. What happens as I move forever to the left and forever to the right on this graph? Here's what you need to know about this. It's all about degrees, meaning squared, cubed, etc. If the degrees match, if the numerator and denominator match, allow me to say top and bottom for numerator and denominator. So be ashamed of myself as a math teacher not using those words, but for the sake of time, if the top and bottom match, as these do, squared and squared, then your infinite limit, your limit at infinity is the ratio of leading coefficients. So in this case, I have 3x squared over 1x squared. In the long run, that's going to become a 3. All that matters is the 3 and the invisible 1. This plus 1 right here, in the long run, is irrelevant. All that matters is the degrees. For other examples, if the top degree is greater than the bottom, then there is no horizontal asymptote, and that means the limit equals, it's going to be plus or minus infinity. We just have to observe. This would be like, a quadratic, a parabola. As you move to the right and left on a parabola, it just keeps getting bigger and bigger or smaller and smaller if it's been flipped over. All right, so we have no limit existing, and more specifically, plus or minus infinity. If the bottom is greater than the top, then the limit is 0 every time. You can see a lot of those. If you have 1 over x squared, those will all approach 0. They will all approach the x-axis as x increases or decreases. That should be going both left and right. So let's check out a picture of 3x squared over x squared plus 1. So here we have the matching coefficients of 2. 3 over 1 is all that matters. So you can see this graph, it approaches y equals 3 in both directions. That's just another visual confirmation of what we found. Okay, so sometimes for limits at infinity, as you go to the left, something different is happening when you go to the right. So how do we know that's the case? Here's an example of that. That's the case because sometimes when you're plugging in big positive numbers, a different result happens than you're plugging in big negative numbers. So let's first just establish this. The bottom of this fraction, the square root of 2x squared plus 1. Can we agree that the negative 1 is irrelevant in the long run? All right, we're talking about x values that are infinitely large, meaning, let's say you plug in x as 100. 2x squared, 100 squared is 10,000, so 2x squared would be 20,000. When x is just 100, much less infinity, this 1 becomes less and less relevant over time. So this 1 is meaningless, meaning the bottom is essentially equal to the square root of 2x squared, which is the square root of 2 times x, if we evaluate the square root of both of those parts. All right? I need you to just understand that the denominator of this fraction in the long run is essentially the square root of 2 times x. The reason that is important is because now we have x to the first on top, x to the first on the bottom. And my limit is my leading coefficients. Now I am approaching positive infinity, which means the top is always positive, and the bottom's a square root. The result of that's always going to be positive. So the limit as x approaches infinity is 3 over the square root of 2, which if you were to type in your calculator, you'd get about 2.12. But 3 over the square root of 2 is fine. Now, if you look this up in a book, they will give you a series of crazy steps that you could learn if you had to, but all those steps can be ignored if you can agree that the denominator is essentially the square root of 2 times x. It's going to save you a lot of time. All right, so ignore the plus 1 and then square root what's left. So how's this next one any different? If we're approaching negative infinity, meaning we're going to the left, the only difference is this top number is going to be negative 3. Because if I put a negative number in for this x, like let's say x is negative 100, I get negative 300 minus 2, or negative 302, while the bottom stays as a positive square root. Same degree, because this bottom is essentially equal to the square root of 2 times x, negative square root of 3 over 2, or negative 2.12. Okay, so when different things happen, like if the bottom, mostly if the bottom's a square root, or if something is squared that makes it always positive, we have to watch out for moving left and moving right having different horizontal asymptotes, meaning different limits at infinity. We're going to wrap it up with this picture. These are the limits we took on the last slide. You can see 2.12 was the number that we were dealing with. That's this line right here is approaching 2.12 as we move to the left, negative 2.12, and this line right here is approaching positive 2.12 as we move to the right. This square root down here is the reason that it was negative on one side, positive on the other side. All right, so that's going to wrap it up for infinite limits and infinity, which are essentially vertical and horizontal asymptotes.